Awesome. We get -1. So here is multiplying the numerator. The numerator is a mess to multiply together, but we'll talk about it here in just a second. So before we multiply this up here, we're going to have, obviously, we're going to multiply what? 2 minus the square root of 5 here as well, correct? So we got to multiply these two binomials together. Now, just to help you out, I'm going to make something up here. A plus B, and we're going to multiply it times C plus D. All right, so you guys know how to multiply this down here together? We take the A and we multiply it here, correct? What do you get? AC. And when you multiply A times the D, you get AD. Then you're going to multiply the what? So I'm going to get BC, and the last one would be, okay? So you're going to get 4 terms, right? Now, what's really nice when we're doing like x plus 2 and 3x minus 4, we're doing something like that. These terms right here, which is the 6x and the minus 4x, match, correct? So we usually can combine our middle terms here when we're doing a polynomial, all right? I'm sorry, when we're multiplying, yes, polynomials together. But this is a square root, so it's a little bit different. So let's do 3 times 2. What do you get? 6, right? Now we're going to take 3 and multiply the next one, which would be what? Minus 3 root 5. You're distributing the 3 to each of those, and then what else will we distribute? The back number, right? So that is going to be multiplied times 2, so I get -2 root 2. And last but not least, I'm going to get this one I got to distribute to the 5. So it gives me -√2 times -√5. Anybody know what that's going to end up being? This is all underneath one root, so it ends up being √10. Okay? Now this whole thing is over what number? So all I'm doing here on this numerator is distributing like what we did over here, okay? The last but not least thing is I got to divide everything by a negative, so I get -6 plus 3 square root 5 minus 2, plus 2 square root 2 minus the square root of 10, and that is the answer to this problem. I told you to go crazy. Now, the reason why it looks really crazy is because, again, we cannot combine the middle terms. They are different, kind of like this one. I can't combine the A and the D and the B and the C because they're not the same, okay? If you, again, when we are multiplying our factors for binomials where we have x plus 5 and x minus 5, then we can combine our middle terms there because we have like, all right? So it can get kind of crazy when you're rationalizing, okay? It's kind of weird to think that this right here that we started with simplifies down to something that looks like that, okay? Just to remove the square root off the bottom, it just goes like weird, right? Yep, that's just the way it morphed. All right, taking a look at the second one there. You're given this. What did you guys notice about all of these? All right, a -5x, which will leave you what? You okay, Murray? Yeah? Just tired? You look like a bicycle. She looks too tired. A little flat, too. So. Hey, what was the most groundbreaking invention ever made? No, a shovel. I'm just trying to bring up the spirits in here. All right, now. So I am pulling the -5 out of 145. How many times will 5 go to 145? 29 times. And what happens to your sign? And that is now x to the what power? Thank you. How many times will 5 go into 500? 100 times. The x disappears and the sign is positive. What do we notice now? I have a what? 1, 2, 3 terms. So you have a what type of trial and error? So this breaks down to a minus and a minus, an x squared and an x squared, and 100 is 1 times 100, 2 times, 3 times 33.333333. No, never mind. 4 times. So I can stop there. 4 and 25. -5x. F of x equals. Now what? F of x equals -5x. All right, so we have conjugate pairs here. All right, go down here. How many solutions does this have? Kylie, how many solutions does this have? Knox, how many solutions does this have? Peyton, how many solutions does this have? Weekly, how many solutions do we have? Lily, how many solutions do we have? Mary Beth, how many solutions do we have? Ian, how many solutions do we have? Kate, how many solutions do we have? Murray, how many solutions do we have? She's just guessing. Kevin, how many solutions? Cheyenne, how many solutions? That sounded like a question. Addison, how many solutions do we have? She's agreeing with Mary Beth. Annie, how many solutions do we have? All right, Chad. Eliam. Ellie. Mathis. Lily. I'm sorry, Lydia. 4. Audrey. Aubrey.
I'm not answering you now. 5.
Overby. 4. Carter. 5. Madison. How many Z's are you counting? Too many. Lily, why is it 5? 5 X's, 5 solutions. Kate, what power is what we started with? Kate? What was the power we started with? What's your highest power? What? I didn't hear you. 5? She's asked a question that wasn't really a statement. 5? What is this power right here, guys? What did I say about that power in the fundamental theorem of algebra? That is how many solutions there are. The fundamental theorem of algebra. This is a theorem, which means it's really, really important. And the one thing out of all of algebra is if you're working with polynomials, whatever that degree is how many solutions we have. So we have 5 solutions. Okay? Now, most of you guys counted 1, 2, 3, 4, but did you miss that? Yeah, that's where you missed it. Okay? So there are 5 x's. When we multiply those back together, we will get 5. Now, here, look, there's 2 there, and 1 there. There are still 5. No matter where you are, there will be 5. Now, when you get into calculus, you're going to break down these. When you start breaking down like an x to the 13th, they will all basically show up into linear terms and quadratic terms. Okay, they'll end up being linear and quadratic. If I had x squared minus 2, we couldn't factor. That would be irrational. All right, well, we could factor under irrational numbers. But in that case here, there is the quadratic formula for those. All right, so some of them end up being imaginary. All right, so depending on your power up here, it tells you how many solutions you have. Make sure you understand that. All right, for those who kind of lost it, because I talked about it the last 2 days. All right, it's okay. I did the same thing in A block, and I had 3 holdouts that were saying 5, and the other ones all said 4, and they didn't break. They held on to their 5. All right, so good job for holding on to the 5. So, all right, now, 5. So I said, now, what does roots mean? Find the roots. I need to find my solutions. How do you find your solutions? Yeah, zero product property. If I gave you the zero product property, and I said, all right, it's ZPP, you would have went, all right, I got to take x plus 2, set equal to 0. I got to take x minus 2, set equal to 0. I got to take x plus 5, set equal to 0. I got x minus 5, set equal to 0. What would you do with this? For those who had 4, what would you do with that? All right, I also set it equal to 0. So 5x is equal to 0. So x is equal to 0 here. X is equal to negative 2 here. X is equal to positive 2 here. X is equal to negative 5 here. And x is equal to positive 5 here. And if you did that one and you did it that way, how many solutions would you count now? There's a reason why I asked the question, because had we did this, then you would have said, oh, guaranteed there's 5, because I see 5 solutions. So makes sense. I asked it first because I wanted to make sure, do you understand the fundamental theorem of algebra? All right? And the answer is no. But that's okay. We got it today. Everybody's going to learn something today. All right? You got it, Kylie? Yeah. I didn't call you Kaylee.
At least you said your name right.
Exactly. I didn't call her like, Aubrey, be quiet.
I'm feeling hurt today by you. First time you laughed in my face about working at me.
It's so funny. It's hilarious. All right.
Like, do I just mean nothing?
Yeah. My order pairs. What's your order pairs?
Zero negative 5. Zero positive. Zero negative 2. Zero
I'm saying them wrong.
5. Sorry.
You're going the wrong direction. So if I can mess your name up, you can mess up my intercepts? All right, yeah, right. Okay, whatever. It's too much fun. All right, now, so here are my intercepts. Anybody know anything special about this one? Raw hair. All right, that is the origin. What's really, really special about it? The what? It's the y-intercept. This point right here is the only point that can be the x-intercept and the y-intercept at the same time. It's the only point that does that. It is very, very special, okay? So if you end up with 0 there, guys, this is plus 0 down here. That is why it is the y-intercept. Remember that last number is always going to be your y-intercept. There it is, okay? All right, what degree is this? What is an x to the 5th power? Quin, Q-U-I-N-T-I-C, quintic. What is an x to the 4th called? It is a quartic. What is a x cubed called? It's a cubic. What is an x squared called? It's quadratic. So I don't know. I said this morning. I said some people forget that x squared is quadratic. X squared reminds me it has 2 teeth. This is Halloween. So quadratic kind of sounds like Dracula in some ways. So I don't know. Maybe you can think of it that's very, very Gothic. Word quadratic is Gothic, and therefore that's exactly what went in my head. All right, now. So what's this one over here? Anybody know what this thing's called? In behavior. In behavior. Now, this is where it is going to, as we go to the right, what is going on with your, and what's happening when we go to the left at infinity. So I'm going to plug in infinity right here into all of these x's. All right. So this is a positive infinity on all of these x's right now, okay? So what is infinity times infinity times infinity times infinity times infinity? It's a very large infinity, correct? But what happens right here? So I'm multiplying it times a -5. So what happens to your very large infinity? Yeah, it becomes really, really, really small. So in this case here, we're going towards negative infinity, which means we're going which direction? We're moving it down. So as we go right, we go down. So the next question would be, what happens as we make these negative infinities right here? That's a negative. We're doing green. That's a negative right there, infinity, and this is a negative 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 infinity. There are 5 negatives. 1, 2, 3, 4, 5. 2 of them make it what? Positive. 2 make it positive. So I end up with a negative infinity. But there is another negative out front, which now makes it a negative negative, which means that we're going towards a positive infinity, which means we're going up. So as we go left, we are going up. As we go right, we are going down. So it's going to go left, we're going up, right, we're going down. So you can see the path it's supposed to go that way. Okay? All right, so we're going to sketch this graph. You have your points 0, 0. 2 and -2, -5 and +5. Bless you. All right, you ready? We said it's starting up here, finishing down here, correct? You got that, Kate? All right, now, Kate, what we're going to do here is we're going to start up here, and we're going to come down through here, pass through this gate, and we're going to turn back up and go through this gate. And then we're going to turn back through this gate, and then turn, go back up through this gate, go back up here, and then come back down, and then finish. See that, Addison? So we got to go from left to right through every single gate, nice curves, no sharp turns. Does anybody notice anything special about this thing? So yesterday we talked about this even function, and we had odd function, and we had neither function. Even functions have what type of symmetry? This has y-axis symmetry. This one is what we call rotational symmetry. Oops, golly, I cannot spell today. And this one also has what we call origin symmetry. Now, why this is special is because this has an O in it, rotation has an O in it, and origin has an O in it, and it reminds me that we're rotating around and around and around. Okay? So take a look at this green one right here. Watch me. Watch it. Bam, there it is. I did pretty good. It wasn't perfect, but pretty dang close. But this one would have what we call origin symmetry, or it would have what we call rotational symmetry. So this is a odd function. Man. didn't want to pick a color. So we have an odd function going on, okay? One other way to look at that, really quick here, just take a look at all of those powers up top. Man, this thing is like jumpy today. Notice that, Knox? Look at that. That is a 1 right there. That is a 3 right there, and there's a 5 right there. There are no even numbers. They're all odd. There you go. It's an odd function. Okay? You good with that? Again, I want you to be able to see it visually. We're going to work with those every single day. We're not going to have to do the test or anything like that. Just want to go through that. If you want to test a test out, you can. It is, for odd, it's negative f of x is equal to f of negative x. Just so you know. I can show that to you. It's taking this one and flipping it left, right, and then taking it and flipping it up, down. So if you reflect it left to right and up to down, you end up in the same exact spot. That's what that did, okay? All right, enough on that. Questions on your homework? We got a lot to do, so let's see what we got on our homework questions. Hopefully you're going through and you're practicing these. Guys, you can get really, really good at quadratics, and this could be a awesome grade on your next test if you would practice. I can give you my password. Yeah, it is B, not a D. It's Aubrey, not D. There you go, bro.
Thanks.
All right. Oh, let me pause this.